All right, so if we're kind of coming back to where we were after Monday. Monday we ended with this look at fireworks. And so we went through and we talked about how they're classified, the kinds of chemical reactions that take place, and how we get some of those colors and effects. The one thing about fireworks that we really didn't get a chance to talk about because we ran out of time was the oxidizer in those fireworks, those chlorates and perchlorates. They do have some additional hazards associated with them. One of the biggest things that is kind of against them is that if they do not oxidize, they are very persistent. Chlorates and perchlorates are very soluble in water and very stable in water when they dissolve. They don't degrade very well over time, which poses certain kinds of problems in terms of if chlorates end up getting into the water, getting into groundwater, they can affect the drinking water supply. And chlorate exposure has been known to cause damage to the thyroid gland, is been known to cause neurological issues, is been known to have interference with growth and fetal development hormones. So affecting young children and also those that are still developing inside of their mother's womb. And for those reasons, the EPA has set the safe daily dose at 0.7 micrograms per kilogram of body weight. So again, if you think back to what we were looking at last chapter, this is a pretty small concentration. Considering some of the other toxins that we were measuring were in milligrams per kilogram as being their safe concentrations. This is micrograms. This is 1,000 times smaller. So, when it comes to chlorates and perchlorates, that is a big issue that's associated with them. And what's even kind of crazier about it when you think is something that reactive being that stable in water. Now, if the solution were to encounter something that is capable of being oxidized, it'll still react. But you gotta think that most stuff that is in groundwater is not stuff that is going to be readily oxidized. Because most of the stuff in there is already kind of in its highest oxidized form. So that's one of the reasons why it's so persistent. Now we make solutions of chlorates and perchlorates up in our labs. They're used for a variety of different purposes. We can use them as solution-based oxidizers in certain kinds of chemical reactions. But on just kind of the environmental scale, pretty safe in terms of reactivity. They're pretty dangerous in terms of, because of their reactivity being stable, their ability to be in their oxidizing form when they get to us is considerably higher. So we're going to move off of fireworks and we're going to talk about other kinds of controlled reaction consumer products. Things like flares, signal smokes, smoke bombs. Now, to combat some of what we were just talking about, a lot of these flares use chlorates instead of perchlorates. And the primary reason is that the chlorates, if they got into the groundwater, are not nearly as dangerous as the perchlorates are. We also see flares using potassium nitrate instead. Potassium nitrate, you might remember, being one of those components in gunpowder. We also can see that in these flares, we will have the use of PVC, polyvinyl chloride. We'll talk more about PVC in the next chapter because it is a polymer. But the idea behind having the PVC there is that it will extend the burning time and make the smoke flare last longer. What is going on in these things chemically is that we usually have a combination of a couple of materials. We usually have something like sodium bicarbonate. Sodium bicarbonate, you know better as baking soda. And there's usually some sort of organic dye in there to give it its color. So if you're thinking about like smoke flares or smoke bombs that you might see, you know, at a commercial site or at a roadside hazard, or even if, you know, those that you might, you know, use at a airsoft rifle range to play capture the flag. The color in those comes from one of the organic dyes. And the carbon dioxide that comes from the reaction of that baking soda, again, think about our reactions of acids and bases in chapter 8. Carbon dioxide is one of the byproducts of the decomposition and reaction of sodium bicarbonate. As those are reacting, sulfur dioxide is also coming out of this because most of those layers contain sulfur compounds of some kind. So you're getting gases formed as these layers burn, and that's helping to distribute the dye, distribute the smoke into a larger area so that it's easier to see. So we're going to move off of flares, and we're going to talk about another group of oxidizers that are common, but probably less common than the ones that we have been talking about. We're talking in this case about ammonium compounds. So ammonium compounds are ionic compounds. They're going to feature the ammonium ion, which is NH4 positive 1. Now, ammonium compounds can give us a wide variety of reactions for them. Now, where we will see ammonium compounds already are kind of known to us. We've talked about fertilizers. We've talked about other kinds of substances. Ammonium ion itself is what is called the conjugate acid of ammonia. So we've talked a lot about ammonia in this class. Well, when ammonia acts as a base, ammonium ion is the result of that reaction. And so the thing with ammonium compounds is because of their roots being tied to ammonia, being tied to other compounds, these tend to be thermally unstable compounds that are forming. And what we will see often in these reactions is that the ammonium compound itself, when it decomposes, is going to give us something that resembles kind of the starting ingredients for how we made the ammonium compound in the first place. So one such reaction might look like this, where we have ammonium nitrate under heat, and it just decomposes back into ammonia and the nitric acid that it came from. That's one possibility. Now, this one is, I mean, ammonia is nasty. Nitric acid is nasty. You've got two corrosives that are forming out of that. But that reaction is less worrisome than a redox reaction, which might somehow get us something that can be potentially oxidizing or explosive. And so in the second bullet point, we could find things like the formation of nitrogen dioxide, or the formation of oxygen gas, or the formation of a number of other kinds of compounds, depending upon what was attached to that ammonia. The other danger, because of the thermal instability, is that the decomposition can happen very quickly at explosive rates. And so, because of these reasons, the Department of Transportation says no, can't transport them by any means. Now, in terms of their commercial use, again, relatively limited because of the instability. Ammonium perchlorate, though. So we're talking about NH4ClO4. Got a combination of two highly reactive ions there. This is the stuff that, well, this is one of the things that is used in the aerospace industry as a propellant. How it works, the stuff decomposes. As it decomposes, it's going to give tons of gas, and that gas is going to be, the expulsion of that gas is what's going to propel the space shuttle. As you might expect, the instability of ammonium perchlorate is causing some eyebrows to be raised, in particular when it comes to ideas of safety. So the aerospace industry has been looking at other alternatives. Tetranitroacinamidic acid has been proposed as a substitute. I'll be honest, I don't know a whole lot about TNAA. But just based upon kind of the chemical formula there, it would have considerably less oxidizing power in terms of its instability, which would make it a safer alternative. Let's talk about some ammonium compounds that we do know. Things like ammonium nitrate. Ammonium nitrate is a fertilizer-grade nitrogen source. This is actually one of the ones that is found in a lot of commercial fertilizers. The nitrogen in the ammonium and the nitrogen in the nitrate will actually give considerable source of nitrogen to the soil, which nitrogen is one of the elements that is very, very commonly needed in soil for promotion of growth. One of the things that gets depleted quite easily in the soil as the soil is being used. Now, for fertilizer grade ammonium nitrate, we often find that it's mixed with ammonium sulfate or calcium carbonate. Those are acting primarily as stabilizers to help keep the ammonium nitrate from decomposing. But even with those stabilizers, the agricultural use of ammonium nitrate is starting to be diminished slightly because there are security concerns. And with terrorism being something that is ever on our radar and our watch list, securing these kinds of modes of potential explosives has become more and more important. Now, ammonium nitrate can also come in other forms as well. Dynamite grade ammonium nitrate is combined with diesel fuel to make it explosive. It could also be added to nitrous oxide. Nitrous oxide mixed with small amounts of ammonium nitrate will give us what we call laughing gas. And in technical grade ammonium nitrate, this is actually the substance that goes into those cold packs. So if you're familiar at all with those instant ice packs, ones where they've got the membrane in them, you pop it, slushes around and goes over your arm or your knee or wherever. The reaction that's taking place in there is actually really simple. It's ammonium nitrate dissolving in water. The need for that package, the air bubble in there is basically to keep the solid and the liquid apart from each other. Once they come together, they form kind of a slush, and the dissolution of that ammonium nitrate is very endothermic, requires a lot of heat, and so the ice pack is really cold. And in that state, ammonium nitrate is pretty stable. So there's very little concern about that being a potential explosion issue or anything like that. In terms of emergency service, ammonium nitrate will melt at 337 degrees Fahrenheit. And at temperatures higher, at 350 to 410, it actually will begin to decompose. If there's a large quantity of it at a fire scene, it can quickly devolve into explosive potential in a matter of minutes. Now, if there is some form of venting that is possible in those situations, that's the best course of action to prevent that explosive potential, because you're giving those gases somewhere to go. We've mentioned this before, but explosions are basically the rapid evolution of gas in a confined area. So if that area stays confined, the likelihood of explosion continues to grow. But if the container is opened in some kind of way, whether it's opening a hole in the ceiling of the building to let those gases out, or finding other means to vent the area, all those things would help limit explosive potential, because the gases would no longer be fully trapped. Now, that doesn't mean that opening a hole in the roof is a guaranteed way to prevent the explosion. If the evolution of the gas exceeds the rate of venting, pressure could still build up enough to cause an explosion, but at least would limit the capability. Give the gas somewhere to go, as opposed to everything. If your job has ammonium nitrate on hand and it is stored in a large quantity, OSHA regulations do come in. In particular, they apply to farmers or other employers who store and use ammonium nitrate in the workplace. They would also apply to the owners or the lessees of any building, premise, or structure in which there is at least 1,000 pounds of ammonium nitrate or more. So we can obviously understand the farmer part because of all the fertilizer. But this would also cover, certain kinds of warehouses, storage facilities, farm supply stores, that kind of thing, where they would certainly have more than 1,000 pounds of the stuff on hand. And what those regulations entail are a couple of things. What does the building look like that stores it? What kind of fire protection is in that building? How is it stored? Is it stored in bags? Is it stored in drums? Is it stored in other containers? Or is it stockpiled? Is it in, an open garbage can? Or in a giant pile in the middle of the floor? There are regulations for all of those storage kinds of concerns. And obviously there are fire protection agencies and limitations and regulations associated with them as well. Now, because of the explosive potential, Homeland Security, DHS does get involved with certain extra precautions regarding fertilizers containing ammonium nitrate. ATF, Alcohol, Tobacco, and Firearms, encourages the ag industry to report any suspicious activities or thefts to local law enforcement agencies, or in certain cases, the federal government. Department of Homeland Security has regulations related to all of the things that would be involved in the bulk usage, storage, and transportation. So, how is it handled? How is it stored? How specifically should you load and unload it? How should you transport large facilities? And in particular, we're talking about waterfront kinds of regulations. And so, because we're talking about waterfront regulations in here, in addition to Department of Homeland Security, Coast Guard usually gets involved in these kinds of things as well. And there was a specific thing on this slide about the Coast Guard. I kind of left it off here because the information wasn't super important to us. But we need to understand that obviously if we're dealing with waterfront transportation, that is going to be a Coast Guard domain as well. So when it comes to bulk quantities of the stuff, the federal government has a specific interest in the name of public safety, making sure that the ammonium nitrate is being handled properly, it's being transported properly, and if any were to be found missing, that they can immediately start to look for the perpetrator. All right, so let's move off of ammonium now and talk about another common oxidizer. That, again, we're getting further away from the ones that we are super familiar with, the ones that are common, but we may not know too much about them. We may not know about their presence. So chromium certainly fits into this category. Now, hexavalent chromium is specifically talking about chromium in the +6 oxidation state. Now, if you remember back to our first lecture on oxidizers last Friday, we talked specifically about how oxidation states, as they get higher, indicate greater levels of reactivity. And in particular, we talked about +6 and +7 being of particular danger because of high reactivity. So when we are looking at chromium in the +6 state, we are looking in particular at chromates, which have the chromate ion in them, dichromates, which have the dichromate ion in them, as well as chromium trioxide and chromium oxychloride, which I'll have to get back to you on a specific formula for those. It's either going to be this or it's going to be another form. If it's the other form, I'll inform you like Friday about or send everybody an email. That's the only one I'm not quite sure of. But all of these compounds having chromium in the +6 state are highly reactive. And for their reactivity, they were actually used as water treatment agents up until about the 1990s. The reactivity was useful enough that they could basically react with the calcium and iron compounds that form scale from hard water that would build up on air conditioners, cooling towers, and the like. But the problem was the chromium would get into the groundwater and it would start making people sick. Or it would become airborne and there would be health effects associated with it breathing in it. And for these reasons, the EPA banned it as a water treatment agent. Chromium compounds of this kind also have a very conspicuous warning label on them discussing their oxidizing potential because it is pretty considerable. One of the places where we can get chromium-6 formation is during certain kinds of hot work processes on stainless steel. So riveting, welding, cutting, grinding, burning, heating, all of these processes on stainless can give chromium in the chromium-6 state as a byproduct of that hot work that's being done. And for those reasons, OSHA regulates the exposure to those compounds for this kind of work in the workplace. Now, for firefighting and EMS, the possibility of getting high exposures to hexavalent chromium during a house fire are actually pretty low. Usually the risks become higher when we are dealing with heat plus some other action. Heating plus cutting. Heating plus hammering or pounding, plus arc welding, plus add a different feature to it. Just the mere heating is rarely enough to produce high enough quantities of chromium-6 to be concerned with. Potassium dichromate is one of these compounds. Potassium dichromate, K2Cr2O7. This substance is a pretty strong oxidizer on its own. We find its use in chrome plating. So what we see in chrome plating is the oxidizing power of the dichromate actually producing chromium that can be cast onto a metal surface, and that's basically what chrome is. Another interesting use for potassium dichromate is actually in the breathalyzer test. So if you get pulled over for a moving violation, and they suspect that you have that you might be under the influence of alcohol, there's a lot of things that they can do. They always can do the field test, walk in a straight line, memorize the alphabet backwards, those kinds of things. But they can also have you blow a breathalyzer. And what that does, how that works, is the alcohol on your breath will actually react with the potassium dichromate, which is orange in color. And with the sulfuric acid that is in the breathalyzer itself, turn it into the green chromium-3, along with some other stuff. Chemical detectors inside of the breathalyzer would recognize how much conversion has taken place and use that to calculate a blood alcohol level. Now, this method is pretty well known. It's robust. It is considered to be generally reliable, or at least reliable enough to have cause to bring someone in, and then they can take a blood test, which is a little bit more accurate for blood alcohol content once inside the police station. Chromium trioxide is also known as chromium anhydride. It gets mixed with water, it becomes chromic acid. This is primarily used for chrome processes, for metal treatment. So we want to make chrome plating. We want to do things like copper stripping from certain types of alloys. We want to do something called making anodized aluminum, or create something that is corrosion resistant. Chromium trioxide is good for that. Chromium oxychloride is particularly nasty stuff. When it reacts with water, we end up getting chromium 3 chloride, we get chromic acid, and we get chlorine gas. So, of these, the oxychloride's definitely the most dangerous. It's also probably the least common, because the byproducts of this are all kind of nasty. Chromium 3 chloride is not particularly like dangerous. It's not a good oxidizer. It's not particularly good as a reducer. But chromium 3 is an environmental kind of concern. It's something that you don't want getting into the groundwater. It has to be disposed of properly. Chromic acid, as we saw in the previous one, has a lot of uses in the metallurgy areas for chroming, for lots of metal treatment. Chlorine gas, Cl2, we know being very, very toxic, but also a good oxidizer as well. So lots of dangers associated with those products in there as well. So when chromium oxychloride comes into contact with water, you got a lot going on there. The water reactive substance, it produces an environmental toxin, a corrosive, and a toxic oxidizing gas all at the same time. Plus, you've got the reaction that's violent anyway going on at the same time. So the oxychloride, really nasty stuff, particularly dangerous. With ammonium dichromate, now we're seeing the combination of things. We're seeing ammonium compounds, which we know to be dangerous. We know to be difficult to work with and unstable. Matching up with a chromium-6, which is also unstable. So the ammonium dichromate is also quite reactive stuff. Where do we see it? Well, certain kinds of pyrotechnics, certain kinds of fireworks are going to need this extra oxidizing power. And so the dichromate is going to be used for that. Its reactivity also makes it good for dyeing, helping to kind of charge the fabric and make it susceptible for that dye to come in and bind to it and change its color permanently. We can also see it used in preparing leather as part of the canning process. Now, one of the decomposition products of this is nitrogen, which in our case is actually, that's okay. Nitrogen is, other than just being a gas and dealing with problems of potentially a large quantity of gas forming, nitrogen is unreactive as a gas. Has to be in very, very special circumstances to get it to do really much of anything. It's not flammable, it's not corrosive, it's not an oxidizer, it's relatively inert. When it comes to chromium compounds, OSHA has requirements around it. The inhalation concentration maximum is 5 micrograms per cubic meter. which again, that is averaged over an 8-hour workday. That is a PEL value. So if you are working in a situation like we described kind of earlier in this series about chromium, where you're cutting into stainless steel or you're doing some welding that involves stainless steel products, there are regulations in place that are meant to protect you against overexposure in that kind of work. 5 micrograms per cubic meter, that's a relatively low concentration. So we only have a few more to talk about. We're not going to get through all of them today. So we're going to end today by going and looking at permanganates. So permanganate ion is the manganese ion, MnO4 -1. And in that manganese ion, we have manganese in a +7 oxidation state. So again, as you can imagine, in a +7 state, if you look at manganese and where it is on the periodic table, you will see that we have taken all 7 of the electrons that are in that outer energy level for manganese, and we have wiped them all away. So manganese is super hungry for electrons in this state. And that is why it is going to be such a powerful oxidizing agent. Now, where we find it most commonly is in its potassium form, KMnO4, which has a very rich dark purple color. In low concentrations, that purple color of potassium permanganate can appear almost pinkish. That's in pretty low concentrations. In moderate concentrations, this stuff is dark purple. Commercially, we can see that in dilute form, solutions of this can actually be used as a treatment for athlete's foot. It can also be used to treat diseases in fish. We've also seen potassium permanganate used to control the growth population of the quagga mussel, which is an invasive species. Basically, how it works is, well, potassium permanganate is really, really reactive. It interferes with the biological systems in those fungi, in those bacteria, in the cells of that mussel, and disrupts them to either slow down their growth or completely wipe them out. And so that's where we're going to stop for today. On Friday, we've got just a little bit to clean up. We're going to talk about some common food additives, actually, in the nitrates and nitrites. And we'll close up by talking about matches and kind of the specific chemistry of the 2 different types of matches that exist before we get into polymers. Have a good day.